Now more than ever, batteries are everywhere. The Nobel-winning lithium-ion battery chemistry, or something similar, is probably in your pocket right now, since this innovation was partially responsible for the surge in handheld electronic devices like cell phones. Batteries also have a big role to play in electrification and decarbonization we need to slow the acceleration of human-caused climate change, from massive batteries storing renewable energy to electric vehicles. This short video, put together by a team of graduate students involved in battery research, will connect some fundamental concepts in electrochemistry to how a battery works. We'll identify important parameters we consider as we continue to work together to improve technology. A battery is a self-contained electrochemical device which stores electrical energy. This cartoon shows a battery discharging, where an electric current flows through an external circuit to do useful work. This electric current is driven by electrochemical reactions at two electrodes. At the anode, an oxidation reaction occurs, and at the cathode, species are reduced, receiving electrons from the electrode. To complete the electric circuit, ionic current flows through an electrolyte between the electrodes. The direction of ion flux depends on the charge of mobile ions and the direction of the electric current, as shown here. When a battery is charging, the arrows in the discharge diagram reverse, and the electrochemical reactions at the electrodes go the other way. So the anode on discharge becomes a cathode on charging.
One of the fundamental figures for batteries is their voltage response as they are charged and discharged. Here we are viewing the charge and discharge profiles of the battery inside a Tesla Model 3. As you can see, as the battery is charged, its voltage increases. As the lithium-ion battery undergoes extended use, shown by the curve sequence red to green to blue, various degradation mechanisms occur which cause shifts in these charge-discharge profiles. Side reactions like SEI growth and lithium plating are the dominant degradation modes in lithium-ion batteries, and among other things, these degradation modes hinder the electrode kinetics with their added resistance. To put these voltage shifts into real-life factors, a decrease in capacity corresponds to a decrease in the range of an electric vehicle, and shifts in the voltage profile affect its acceleration. In this video, we'll present the mathematical model which can describe these effects in shifting charge-discharge profiles. Compared to lithium-ion batteries, redox flow batteries are less suitable for mobile applications and more suited to stationary energy storage. Redox flow batteries differ from conventional batteries in that their electrolyte is stored in tanks and pumped across the membrane. This flow of fluid is what gives them their name. The inherent benefit in this battery configuration is that the capacity and power of the battery are decoupled from a design perspective, since the size of the electrolyte tanks is the primary factor for the battery's capacity, and the membrane area is the primary factor for tuning the power of the battery. Redox flow batteries are especially helpful in explaining electrochemistry fundamentals because their voltage profiles are nearly what you would expect in an ideal model. In this figure, we are varying the current of the battery during charge and discharge, where the different currents are shown in the legend. Here, the lines above 1 volt are for charging and those below 1 volt are for discharging. There is a clear trend of more drastic voltage response with higher current rates. The shifting of these voltage profiles with current rates can be explained through the Butler-Volmer equation, which we'll dive into next.
In order to understand the relationship between potential and current in an electrochemical cell, the Butler-Volmer equation is often used. One basic version, which can be derived from rate laws and the Nernst relation, is shown on the left, where current varies exponentially with potential. By replacing concentration fractions using relations of concentrations to ratios of current to limiting current, the equation on the right can be derived. The limiting current, anodic or cathodic, can be defined as the highest current possible due to mass transfer limits, which can be considered as how fast a species can be oxidized or reduced, depends on how fast it can be brought to the anode or cathode surface. Lastly, by assuming alpha equals 1/2, we can replace exponentials and combine them into an inverse hyperbolic sine term. Then, by adding a term for ohmic resistance, which could be due to resistances from electrolyte for ions to flow, we arrive at this equation on the bottom right, which we'll use to examine different physical parameters' effects on current voltage profiles.
The first variable we examine in this voltage-current relationship is the effect of ohmic resistance within the battery. holding the limiting current and exchange current densities constant, we see that the slope of the linear portion of the curve profile increases as we go to higher ohmic resistances. This means that a battery with a high ohmic resistance will require a much higher overpotential to achieve a large current density. In a battery cell, where electrons are flowing through an external circuit, there must be a net flux of cations or anions to complete the circuit. If you're wondering where ohmic resistances come into play in a real system, it is due to the combination of the ionic resistance of the electrolyte and the electronic resistance of the electrodes. An additional component, not shown here, is the ionic resistance due to the separator, which lets ions flow between both sides of the battery, while preventing any flow of electrons, which would lead to a short circuit. Next, we look at the effect of the exchange current density. This term describes the current density in the absence of net electrolysis and at zero overpotential. It reflects the intrinsic rate of electron transfer between a redox-active species and the electrode. For any redox reaction at its equilibrium potential, electron transfer processes continue at the electrode-electrolyte interface in both directions. As we can see here, an electroactive species with a larger exchange current density shifts the voltage current profile to lower overpotentials. This means that a species that exhibits kinetically facile electron transfer can achieve higher current densities while requiring less overpotential, in comparison to a system that exhibits sluggish electron transfer rates. The final variable we examine is the limiting current density. This is the maximum current density possible for a given set of mass transfer conditions, because at this limit, the electroactive species is being oxidized or reduced as fast as it can be brought to the electrode surface. We can see that as the limiting current density is increased, higher current densities can be achieved for a given overpotential. Improving the mass transport properties in batteries is therefore crucial whenever high current densities are desired. Engineering improvements are typically sought in the design of electrode and cell geometries and electrolytes with tailored mass transport properties.
To summarize, let's go over each effect on current voltage relations and how to improve them. Ohmic resistance, which controls the linear portion of the curve, can be reduced through increasing material conductivity, which can be done by adding a supporting electrolyte. For exchange current density, which shifts the profiles vertically, you can work with materials with faster kinetics, or consider catalysts. Lastly, with limiting current, which shifts curves horizontally, consider careful engineering or operational options like flow rate or paths in a flow battery, or electrode separation distance in a solid battery. Lastly, when your electrons work hard, you can play hard. Now that you've learned how to create useful batteries and optimize their parameters, go out there and make some electrochemistry. Thank you for your time.